In section 6.3, we're talking about linear and angular speed, and actually this is the third part of section 3.6. We're going to be using angles to model and solve real-life problems in this part of section 6.3. First of all, we're going to talk about arc length. Arc length is going to be the length of an arc of a circle with a radius of r. So if you see a radius r here, that's determined by central angle theta in radians. And so here's theta. Okay, so let's say we want to find this green arc length here. Okay, and I think the easiest way to think about this is if you think about, okay, we know that formula for circumference is 2 pi r. This 2 pi right here is the part of the circle that we're moving around. So if you think about the full circle being 2 pi, well, we're not traveling that full 2 pi radians, that being the angle measure. So arc length, our L, is going to be theta times our radius. So when we're looking for circumference, we're looking for the full circle, and that's why we use the 2 pi. So when we're talking about this portion here, that's why we're using whatever that angle measure might be. It might be pi over 2 times the radius, whatever it may be. But the theta is going to be the measure of this angle here to find this arc length here. Okay, we're talking about the distance around the traveled around the circle. And then let's look at an example. So we've got a circle that has a radius of 4 inches. And we want to find the length of the arc intercepted by a central angle of 240 degrees. So a 240 degree angle is going to fall in the third quadrant. Because if we look at this on here, so we have the angle starting here. Let's put it in red. Let's put it in red. Okay, so the angle starting here, so we go to 90. And then we go to 180, and then this would go to 270. So it's somewhere in here. So let's say this is, and so we're looking for this arc length here. All right, so first of all, our formula that we use that our length is going to be theta times the radius, and theta needs to be in radians. So the first thing we need to do is say, okay, well, we've got that 240 degrees. We need to change that to radians, so we're going to multiply by pi over 180. Okay, and then once we do that, we're going to multiply by our radius, which we know is 4. And then we just need to simplify that. And our angle, we'll find out that when we simplify our angle measure, we're going to get 4 pi over 3, which you don't have to simplify to that. You could just go ahead and do the same whole thing, but the 240 is equivalent to the 4 pi over 3, and then that's going to give us 16 pi over 3, and that's going to be inches, of course. So this route here is going to give us 16 inches. A little less than the circumference of the circle there. That's also about 16.76 inches. All right. Now let's talk about linear speed. For linear speed, we're actually going to use the arc length that we talked about in the previous slide. So if you have a particle that's moving at a constant speed along a circular arc, like for instance, if you think about the hands of a clock, and or if you think about maybe a merry-go-round or something like that, if it's moving at a constant speed along the circular arc of the radius with the radius r, L being the length of the arc traveled in a certain time t, and I've got time here, this should be time, then the linear speed of the particle is given by this equation that I have here. So let's take a look at that. And which this should make sense, because arc length is just a distance traveled. Distance divided by time is going to give us our speed, sort of just like the distance equals rate times time formula. So it's our arc length divided by our time is going to give us our linear speed, and that's all we need to think about. So we have our arc length, that would be our arc length, and then we would just divide it by the amount of time it took to make that move. And this, of course, the arc length is along the edge of the circle. And then we have angular speed. So angular speed is talking about something different. If Theta is again the angle measured in radians corresponding to the arc length. So let's think about this. So we have a circle, and this time we want to know angular speed. So what we're doing this time is not, we're not trying to figure out how quickly, it's moving along the edge of the circle. Instead, what we're trying to do is figure out how quickly this theta here is changing. So angular speed is going to be our central angle measure, which is our theta, divided by our amount of time. Okay, so linear speed, to sum it up, is going to measure how fast a particle moves around the edge. So we've got linear speed, and what linear speed is going to do is it's going to measure how quickly something moves along here. Okay, it's going to measure that speed. And then you've got angular speed, and what angular speed is going to measure is how quickly this changes, this angle. Right, so that's the difference between the linear and the angular speed. And now we're going to try a few problems here. Let's say the second hand of a clock is 8 centimeters long, and we want to find the linear speed of the tip of this second hand. All right, so because we're talking about a clock and we're talking about the second hand, there's a certain amount of information that we already know. So let's say this is my second hand here, and that of course is at the 12, and then we've got 1, 2, let's say it goes from, let's just put it in standard position and say it's going from here to here, and of course it's moving clockwise, so it's a little different, but let's just think about the distance that it moves here. So what we need to figure out is how long it's going to take that to happen. All right, so if you think about this angle going from 3 to 12, whichever direction it may be going, that is going to be pi over 2 radians there, and it's going to take us, well, if the second hand moves all the way around the clock, once it moves all the way around, that's 60 seconds. So a fourth of the way around, like we have here, is going to take us 15 seconds. Now, you didn't have to use the pi over 2. You could have also said, okay, pi, and it could have gone to the 6 and chosen to use 30 seconds. So either way is fine. So pi over 2 is going to take us 15 seconds to make that move. All right, and so what we're trying to find here is the linear speed, okay? And let's think about what we know about linear speed. We know that linear speed is going to be our arc length divided by our time, okay? And if that's the case, then our arc length is just going to be our pi over 2 times our 8 centimeters, which is the length of this second hand. Okay, and so that's going to give us our arc length, and it's going to take 15 seconds for us to produce that arc length. So we divide by the 15, which is our time. And so we just simplify that. And when we do, we are going to end up with 4 pi over 15. And since we're talking about the distance it travels, then this is going to be centimeters, because the length of our hand is in centimeters. We've got 8 centimeters. 8 centimeters per 4 pi over 15 centimeters per second. Okay, and if we wanted to look at this as a decimal, that's at about 0.84 centimeters per second. Okay, again, so we have the arc length here, arc length, and we get the arc length by taking our angle theta, which in this case was pi over 2. We just chose one randomly, times 8, which is going to be our radius, over our amount of time, which is here, just 15. Okay. And now let's look at the next example. This time we have a circular blade on a saw. It's going to rotate 2,400 revolutions per minute, and we want to find the angular speed in radians per second. All right, so we're going to start with what we know about the angular speed. Okay, we know the angular speed is going to be our angle measure in radians divided by our amount of time. So it doesn't tell us a certain, but it tells us it makes 2,400 revolutions in 1 minute. So let's say we go, instead of talking about 2,400 revolutions, let's say we say 1 revolution, which in radians, 1 revolution around a circle is going to be 2 pi. Okay, and the amount of time it's going to take to do that. Well, that's going to take a little bit of work over here on the side. So let's do some side work. We've got 2,400 revolutions because it wants us to find per second here, we're going to change that 1 minute to 60 seconds. Okay, and then once we do that, that's going to tell us that we get 40 revolutions per second. All right, well, that's revolutions per second. Well, what we want to know is, since we start out with our 2 pi, is we want to know how long it takes to get 1 revolution. Now, you could set up a ratio, or you could just recognize that this is going to be 1/40th, either way. So if you get 40 revolutions in 1 second, then you're going to get 1 revolution. Let's just abbreviate here. 1 revolution in 1/40th of a second. Okay, again, if you can't make that connection immediately, then you can say, all right, I've got 40 revolutions in 1 second, and I want to know how long it's going to take me to get 1 revolution. Okay, and you're finding x, and that's going to produce this 1/40th here. All right, so my time then, I come back over here, and this is going here, so 1 over the 40. And when I simplify this, I'm going to get 80 pi radians per second. Okay, and it's radians per second because we're talking about the speed of the angle, how quickly the angle is changing. So we're talking about radians this time, whereas last time we were measuring in centimeters. All right, now we're working with that same problem, and we are being told that the blade has a radius of 4 inches, and we want to find the linear speed of the blade in inches per second. Okay, so let's think back to our linear speed. It's going to be our arc length divided by our amount of time. Okay, and so what is our arc length going to be? Last time we went with 1 complete revolution, so we'll do the same thing this time. 1 complete revolution is going to be 2 pi radians, and it's going to be times 4. So you notice this is the same as taking the circumference of that circle, and it's going to take us 1/40th of a second to do that. And so we simplify this, and that's going to give us 320 pi, and this time we're inches per second. All right, and that's all I have for section 6.3.